Hello and welcome to the first video of the FP1 chapter series. Start a question on the screen to review some GCSE work. Calculate the 50th term of these sequences. So here we've got an nth term, 5n plus 2. We just replace the n with 50 and we get 5 times 50 plus 2, which is 252. The second one is called the rth term, but it works in the same way. And I'm going to use r and n because r is quite well used in this chapter, but it does pretty much the same thing. So this one, we replace the r with 50, and we get 2 times 50 minus 101, which gives us minus 1. The third one is another nth term, but here I've got un. This just means the nth term. So u is standing for term, and the little subscript n here tells you which one. So if I want term 50, I can write this as u subscript 50. And then I replace the n with a 50 as usual, and here we get minus 150. The last one, very similar, the rth term. We replace the subscript r to show it's the 50th term, and we get minus 100 over 50, which gives us minus 2. I hope these are familiar to you from your GCSE work. We're going to be using this idea in this chapter. An overview of the chapter. In this video, we're going to know and use something called sigma notation to find the sum of n terms of a series. And in the next video, we're going to take on that to two particular formulas, which is the sum of the squares and the sum of the cube numbers. So a sequence, just to review some things you should already know, is a list of terms, often numbers, that follow a pattern. And the terms are separated by commas. So here we have a sequence, we're adding 3 each time. This is an arithmetic sequence, and you could find the nth term, which would be 3n minus 1. A series is subtly different. It's a summation of terms of a numerical sequence. They're being added together, so it will have the same numbers, but it will have a plus instead of a comma. So we add these terms together, and this is a sequence, but this is a series. Now obviously if we added all of these up, we kept going the dot 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 here, this would just be an infinite series. You would never get a final numerical answer. But if we know a starting point and a finishing point in the series, then we can evaluate that to find a final numerical answer. For example, if we summed this from the first term to the third term, then we would get the answer 2 plus 5 plus 8, 15. So this is the sort of thing we're going to do, but we need to find a way of doing this without a lot of words and without a lot of horrible calculations. To help with this, we use capital sigma, which is this symbol, to indicate the sum of a series written in rth term form. The reason we don't use n here is because we're going to use n as part of this, meaning something slightly different. So here, this means the sum of this sequence with this rth term, so that would be the formula for the sequence, 3n minus 1 or whatever it is. And at the bottom here we've got r equals a, and a will be a constant. Often it will be a 1, but it doesn't have to be a 1, and that's telling you which term to start your summation. So if r is equal to 1, then you're starting with the first term. If r is equal to 5, you're starting with the fifth term. And n here, instead of being the nth term, we've got the rth term, so that the n indicates the final term where to stop your sum. So if this is r equals 1, and then this number here is 5, it's telling you to start with the first term and finish with the fifth term, so you would be summing the first 5 terms of whatever this sequence was. So this is the general form. A couple of quick examples to emphasize how this works. So this is saying sum, so add together the terms of this sequence, which of course will be a series when we're summing it. Start with the first term, finish with the third term. So I need to know what the terms of this sequence are in order to add them together to get the series. So the first term, where r is 1, we'll put that in, 6 plus 1 is a 7. The second term of the series, where r is 2, 12 plus 1, 13. The third term, where r is 3, 19. And if it was an infinite series, we would keep going, ... but we need to stop here at the third term. We only want 3 terms. So this is it. And then I can do that, evaluate this, and I can get 39 as my final answer. Another quick example. Here we're going to start with the second term of the series, stop at the 6th term, and our series is just r. So this is just the natural numbers. If r is 1, that's 1. If r is 2, that's 2. So it's just 1, 2, 3, 4, 5. And we're summing them. So we're starting with r equals 2. And then we go all the way up to the 6th term. So that was the second term, the third term, 4th term, the 5th term, and the 6th term of the series r, which would normally start with a 1, but we're being told start with the second term. And then again, you just add these up and get your answer, 20. And that's quite straightforward with the calculation here, but I hope you can see that this is going to be a lot more complicated if this number here was, say, 103. You wouldn't want to have to write out 103 terms, add them all together by hand or by calculator. So there are some things that we're going to look at to make this a bit easier when this gets more complicated. And a few standard sums to help us out here is if you sum the series 1 from 1 to n, so it's just 1 plus 1 plus 1 plus 1 plus 1 n times, then I hope you can see that you get the answer n. That maybe isn't all that useful, but it's a precursor to this one, which is far more useful. Any constant k, if you sum it from the first term to the nth term, you'll have n lots of k, which is just k times n. The last one, the summation from 1 to n of the natural numbers r, so this is a series we had on the previous screen, 1, 2, 3, 4, and so on. This is a more complicated formula, and it's one that you should just remember. We'll talk about proofs in the next chapter, but for now, just remember this and use it. And it's a half times n plus 1. So here are 3 standard sums that are going to be very useful. We'll look at a couple more useful properties later in the video, and we'll be using all of these to help solve some problems. So a few examples with these first. Evaluate the sum from 1 to 5 of 3r plus 2. Okay, so here there are only 5 terms, so I'm just going to write them out. So we've got 3 times 1 plus 2 is 5, 2 times 3 is 6 plus 2 is 8, 3 times 3, 9 plus 2 is 11, and by now you can probably see it's an arithmetic series adding 3 each time, so we've got 14, and then the 5th term is 17. And I only want the first 5, so I need to stop there. Then we go ahead and add these up. Don't have a calculator, my mental maths is not great, so we've got 10, 20, 30, 42, 55, I hope. But this second one is going to be more complicated. We're going to need to use the formula here, because from 1 to 40, I don't want to write out 1 plus 2 plus 3 all the way up to 40, and I don't want to have to do that mental calculation, especially without a calculator to hand. So we're going to use the formula. So it's a half times n, which is 40, times n plus 1, which is 41. Half of 40 is 20, so that's 820 as a final answer. The last one here is a bit more interesting because we don't start at the first term, and obviously I can't just use the same formula here to get this one, because if I use the same formula with the same n, I would get the same final answer, and that can't be true because we're starting at term 21, so we're dropping off the first 20 terms. So obviously I can't get the same answer for this sum. So what I need to do here is I need to first find the sum of the first 40, which I've got here, then find the sum of the terms I don't want, 1 to 20, and subtract it. So let me write out what I'm doing here. This is a useful property. It's going to come up on the next screen, if you'll forgive my terrible Sigma drawing. We're going to sum from 1 to 40, and then we're going to sum from 1 to 20, and then take away the first 20 terms sum from the first 40 terms, and that will give us 21 to 40. So I've got two stages here. We've got a half times 40 times 41, which we already know is 820, and then minus a half times n for the second summation is 20 times 21, and that gives us 10 times 21, 210, which gives us a final answer of 610. And obviously that's much easier than starting with 21, going up to 40 and adding each term in between by hand. So that last one there is an example of this, which is really, really useful. If a sum starts at r equals a, where a is not 1, you've got to first start at 1, go up to n, then go from 1 to 1 less than where you want to start, because this one wants to include a in my terms, and this one will include up to a minus 1, but it will leave the a behind, which is what we want. So this is the general form of what we just did in that final example on the previous slide. There are a couple more properties that are very useful. Here they are. This is saying that if you've got a constant times by a sequence in the summation, because that constant will be on every term, you can effectively factorize that out and bring it outside of the summation. So you can do the summation first and then find your answer and just multiply your answer by k instead of having k on every individual term. Down here we've got the idea that if you've got two elements to your sum, or if you've got two summations separately here in one sigma, you can split that into two sigmas. So you can sum this one, and then add your results together rather than doing them together within the summation. These are all things I'm going to use in the following examples, and I think it's easier to see why these are useful as we go through them. So I've got those at the top there. Show that from r is equal to 5, starting at the fifth term, up to 2n minus 1, this term, summing r, which we've got the formula for, there it is, that we will get the answer 2n squared minus n minus 10 if n is greater than or equal to 3. So let's just check what's going on here. If n is equal to 3, that gives us a 6 minus 1 is 5. So from 5 to 5, that will just be the fifth term by itself. So that's okay. If n was less than that, we would have a number here less than 5, and that number on the top cannot be less than the number on the bottom. We can't start at the fifth term summing up to the third term because the third term is not above the fifth term. But as we increase this, if this is 4, we get 8 here, minus 1 is 7. So this will always be an odd number. We're summing from 5 to 5 or greater odd numbers. So the fifth term to the fifth term, or the fifth term to the seventh term, or the fifth term to the ninth term, etc. None of that is all that important, but I want to show that this does make sense. We're not doing something silly here because of this little caveat on the side. So what I'm going to do is just put in the formula for this sum, and we're going to use this first of all, because we're not starting at 1, we're starting at 5. So this needs to be the sum from r is equal to 1 up to 2n minus 1 of r minus the sum from r is equal to 1 up to 4. Not 5, it's a common mistake to put this number here, but we want 5 included in the sum. And this is going to take out all of these terms. So I want to take out the first 4 terms, and I want to leave the fifth term in. And that is still r. Okay, now I'm going to apply this formula here. So we've got from r is equal to 1 to 2n minus 1. So I've got a half times little n. In this case, that is 2n minus 1. And then n plus 1, little n plus 1 in the formula, here is 2n minus 1 plus 1, which is just 2n. And that's the first one. From that, we're going to subtract from 1 to 4. So here n is just 4. It's a bit easier. Half times 4 times 4 plus 1 is 5. So that's a 10. So this bracket is the minus 10 on the end. That's good. We need a minus 10. And this bracket here, half times 2n. I can cancel those nice and easily. And then I've got n times 2n minus 1, which gives me 2n squared minus n, which is the answer we needed. So there I've used this one and I've used this one. In this example we're going to use a few more of these. We're going to use the blue one and the purple one. So we're evaluating from 1 to 20 4r plus 3. So here I need to use this first of all, because I've got two separate terms, 4r and a 3, here and here. So I can split these into two separate summations, a 4r and a 3. So let's split that. We've got r is equal to 1 to 20. We're not changing that here. We're just doing a 4r and then plus r equals 1 to 20. That stays the same. 3. So I've just put the two terms in two separate summations. The reason I'm doing that is because this one here, hopefully you remember, we can use this. Summation of k, here 3, plus 3, plus 3, plus 3, plus 3. The r doesn't change anything, this is just a constant. So we're going to add 3 20 times. That's just 3 times 20, which is, of course, 60. On the other one, for r, I'm going to apply this rule here. K times an r formula, I can bring the k, here the 4, outside the summation. And the reason I'm doing all of this and didn't just play with this is because I don't know a formula that will sum this for me very easily. I would have to write out all 20 terms and add them together. Whereas I do know a formula for just r by itself, it's this one here. So that's the reason why I'm pulling this apart. So we've got 4 times the summation from 1 to 20 of r, and now I can apply the formula here for that summation for r. So we've still got the 4 in front, don't forget about that. And then we've got the formula to sum r from 1 to 20 is a half times n, which is 20, times n plus 1, 21, and I still have that 60 on the end. So here I'm going to cancel this to make 10. Is that sensible? If I've got poor mental maths, I would probably do 4 times 21 next is 84, 840. Plus the 60 on the end gives me a nice round 900. And there we go. We've used quite a few. We've used the blue one, the purple one, and these two yellow ones here. Final example. Show that the summation of this is equal to this. Now here we've got a formula for this sum, so when we come to evaluate this, because you can see it's the same thing, we're just going to use the formula. But I wouldn't have known this formula if they hadn't told me, or if I could not work it out for myself. So you won't be expected to know formulas like this for any random summation. There are some that you're expected to know, i.e. these two here, and there will be some that you've got on the formula sheet given to you, which we'll talk about in the next video. But generally speaking, you won't be expected to know this sort of thing. Either it will be part of the question to work it out, or they'll tell you. So here we need to work it out for ourselves and prove that this is true. I'm going to do something very similar to what we did on the previous one. I'm going to split it first into two pieces, 7r minus 4. The minus 4 is a constant, I'll use this. The 7r, I'll apply this to bring the 7 out the front, so that it's just an r in the term, and then I'll apply this formula And hopefully by the time we've done all of that, we'll be able to tidy it up to look like this. So here we go. This is going to be equal to, or let me be a little bit clearer there. This is equal to summation 7r. I could probably bring the 7 out as part of this stage as well. I think the examiner will be fine with that. And the 4 there. So then I've got 7 times r from 1 to n, which is just my formula. Half times n plus 1. We don't know what n is here, so we're just using the actual little n. Minus 4 from 1 to n, using this property, is just 4n. And now I just need to tidy it up. So we've got 7 over 2 n squared plus 7 over 2n minus 4n. If I want to put that in the same fraction, I've got 8 over 2. So that's minus 1 over 2. And if I pull the half out the front to make it look like what they want, and pull an n out as well, that leaves me with 7n minus 1 as required. So we've shown that this is true. This formula will work for this summation, only for this summation. Now I need to sum from r equals 20 to r equals 50, so now I'm applying this one here in green. We need to go from 1 to 50 first, and then go from 1 to 19. Remember, we want to include 20 in this sum, so I go from 1 to 19 and subtract those terms away. So we've got the sum from 1 to 50 of 7r minus 4 minus the sum from 1 to 19, 7r minus 4. I'm stressing that because it's such a common mistake to put this number here. It needs to be 1 less than that. And to do this, because we've got the formula now from part A, we're just going to apply this formula. 50 for the first term, and then 19 for the second one. So we've got a half times 50 times 7 times 50 minus 1, 349. That's the first one. Minus a half times 19 times 7 times 19 minus 1. I am going to have to go and get my calculator to get this final answer. So this is 132. And then if you put all of this on your calculator, the answer you should get is 7,471. And that is the end of this video. There are some formulas here that you should remember. You should remember this, this, and especially this one. But there are 3 properties as well that you'll need to remember here. In the next video, we'll talk about 2 formulas for slightly more complicated series. However, they will be given to you in the formula booklet. You won't need to remember them. So helping to remember these are the questions from exercise 7a. You can attempt these now if you've got access to the textbook, and maybe I'll see you in the second video.